Okay, so in chapter 10, we're going to be looking at hypothesis tests from tables. We're going to start off with 10.1 looking at goodness of fit. And just to recap a little bit, this is a chi-square distribution. If you recall, this one is not normal. However, the larger the sample size, the more normal it starts looking. And our mean is typically slightly to the right of the peak, usually. And our distribution here is we write our subscript of our degrees of freedom. Specifically, for the goodness of fit, to get our test statistic is a summation of the square of the difference of observed minus expected divided by the expected value here. And so our observed values is what we get from our actual data. The expected is kind of the theoretical, what we would think we would actually get here. And we'll look at an example here that'll show us how to calculate this. So, and goodness of fit is always going to be a right-tailed. Okay, so here we have an example. So employees want to know which days of the week employees are absent in a 5-day work week. So they asked 60 employees here, or they asked, random sample of 60 managers who were asked on which days of the week they had the highest employees absent. So here's the results listed here. Okay, and so first off, let's see here, is that we're trying to find out the absences, if the absences occur with equal frequency. So again, we're talking frequency, which we could always turn into a proportion. If you remember back in chapters 1 and 2, we could always get our relative frequency. That's always ends up being a proportion. So this is going to be dealing with proportions, and there's more than 2 groups. So we're doing a few groups here. And so this is going to be a goodness of fit test. And so this is what we call the observed. And here we have our expected. So when we actually collect our data, we observe for Monday there's 15, Tuesday 12, etc. Now we're trying to see if this from the sample of 60, we're seeing that they all have equal frequency. So we just divide that by 5, and so we'll get 12 for each single one. So that's what would be expected if it's the same across the board here. So again, goodness of fit compares proportions, okay? Or we could say frequencies, because we know how to go back and forth from each of those. So technically, if we wanted to talk about it in terms of proportions, it would be 12 out of 60, right? It would be 20% of each of those. Sometimes it will give us the information in proportions, and we'll have to calculate that. And at the end, I'll show an example of that as well. But it's just going to be a fairly simple case. And again, one thing is that here, notice we'd have more than 2 groups. So we're looking at 5 days of the week. So whenever we're looking at more than 2, we're going to start using tables to kind of get that data. Okay. So our first step is the null and the alternative here. And if you recall, the null is always saying that they're the same, that they're equal, and the alternative is that it's different. So in this case, we'll say not equals. And that's just an easier way to remember it. So we're going to say that the absences occur with equal frequencies. And here we're going to say that absences occur with unequal frequencies. And so the null ends up being our claim this time around. And sometimes you might see this with more mathematical notation where proportion 1 equals proportion 2 all the way up to proportion 5. So sometimes you might see it written in that way. And again, if we are doing proportions, then you're not going to want to use the frequencies. Your expected would actually have 0.20, 0.20, 0.20 for all of them. So sometimes you might see people do the test where they turn everything to proportions. However, we know we could go back and forth. Since everything's already in frequencies, it's going to be less work to leave it like that. Okay, so let's go to our second step here. And this is our stats and data. And really, everything's kind of here in a table already for us. List 1 is going to be our observed. And list 2 is going to be our expected. Okay. If you're using the 200B program, I think it might end up swapping those. But if you're using your goodness of fit that's default on your TIs, it should be list 1, list 2, observed, unexpected. And we'll talk more about that when I show you how to do the calculator. But let's get into step 3. So calculator, the calculations in graphing here, okay? And so some key things here is that, again, it's not normally distributed. This guy is kind of skewed off to the right. And it's going to be right-tailed. These guys are always going to be right-tailed because we're seeing that it either occurs with equal frequency or it does not. Okay, and so here's kind of our quick sketch there, and then I'm shading in our critical region for now. And we're starting at 0, as opposed to 0 being right in the center. And so what we're interested in here is going to be, again, our chi test statistic, also a critical value, the alpha, and then a p-value here. And so if we plug this into our calculator, and I'll show you where to go into the test on this on the next slide, but it's just you go under your test, and it's the goodness of fit, and we'll input our information. And it's going to give you your p-value and then the chi-squared, that test statistic of 3 there. And here's our alpha of 0.05, in the critical region. And so the question is, where exactly should we have that test statistic, right? So we got to look at the p-value, which is more area. So that means alpha is going to be contained within the p-value. So to kind of finish our little sketch here, so that means the test statistic is somewhere over here in this region. And then all of this is the p-value, encompassing both areas there, both of those regions there. And so again, it's larger than alpha. So alpha is contained within there. And what is that actual cutoff where we draw our line in the sand right here? That's that chi-squared critical value. And we could actually get that using the 200B program, if you have that. Otherwise, you technically don't need it because we could compare the alpha with p-value to make our sketch. But it is a lot easier to compare the two different chi-square values because we know 9.5 is going to be further to the right than 3 since 0 is over here at the start. So that's the benefit of calculating those, and you'll need the 200B program. I don't think the 83s or 84 do that by default. And so our fourth step is going to be our discussion and conclusion here. Our p-value is larger than alpha, so we don't reject the null. That means we reject the alternative. And in this case, as we said, the null and the claim are the same. So whatever decision you made for the null, you're going to make for the claim. So do not reject the claim here. And since the claim is the null, we are not allowed to use language like we support or do not support. So this is going to be where we use that warrant rejection language here. So we would say there is not sufficient evidence to warrant a rejection of the claim that absences occur with equal frequencies. So there's not sufficient evidence to warrant a rejection, right, of the claim. So we're kind of saying we're agreeing with it. We're kind of in favor of it. But again, you don't want to say you support. Okay, I want to be very, very careful with that. Okay, and so this is our four-step process for the chi-squared goodness of fit test. So here I want to show how we actually get that chi-square test statistic. I'm doing it by hand, and so we're going to be looking at the formula that's given here. And so let me just call this observed, and I'm going to call that O, and then we're going to do our expected. So we had this from the table before there, and what we want to do, we want to extend this table out, and I'm going to go ahead and worry about the inside here, what's in parentheses. So observed minus expected, we're going to want to do that. And so we're just going to observe minus expected. So 15 minus 12 is going to give us 3. And we're going to do this all the way down the line there. And notice some of these become negative values. So when we do summations, we want to make everything positive. So that's where the square comes in. So we're going to go ahead and square all of those values. And these guys are not always going to be the same, right? These numbers here to get us exactly the same values in this column. That's just a coincidence that it worked out like that. Just work out the numbers, whatever they are. And then one more, let's add another row here. And so what we're doing here is we're going to do our answer before, which is going to be this here, the observed minus expected squared, and we're going to divide that by the expected, which is 12 right there. So that's where I'm getting 9 over 12. And we're going to do this for each of these columns here. Okay. And again, they're not always going to end up being the same values here. In this case, they are. And then we want to deal with the summation, right? That's what that sigma means. So we're adding across here. So 36 over 12, which gives us 3. And that's how we get that test statistic, like chi-square test statistic. I want to show what I actually plugged in to run the test. So if you notice in list 1, I put my observed, and in list 2, I went ahead and put the expected values there. And then we actually run it, and it's a goodness of fit test that we're going to run there. And it will spit out your p-value and then that test statistic 3. So this is exactly this whole calculation here. So that's where that 3 came from. One thing you do need to input is your degrees of freedom. Our degrees of freedom here is 4. Since we have 5 different groups, 5 days out of the week, it's going to be n minus 1, so 1 less than the actual group. So our degrees of freedom give us that value of 4 there. Okay, and so here is another example. And the chapters are different because this is from the original text here. But just to kind of look at it, I wanted to do an example where those frequencies are not necessarily given to us here. And so if we see that the observed here, and then we have our expected, okay, for these guys. Let me actually write in a different color here. Okay, and there's kind of a mismatch where this is in percentages and then this is in frequencies. And so we want to make sure that everything is exactly the same. So I'm going to convert this percent into frequencies, okay? And so what we want to do here is we're pretty much just going to multiply. So we're going to have 18% times 1,000. And again, the 1,000 is coming from the total observed here. So when we look at our observed data here, if we add all of these up, we get a total of 1,000. So we're multiplying our P times N pretty much. And so that's going to give us 180. And we're going to do this all the way through for all of these. And this is actually going to now give us a frequency. Again, sometimes you run them as proportions, but here we're going to put everything in frequencies so that they're consistent. So our expected is going to be this right here. And then our observed will be these values right here. That'll be what we put into our list 1 and list 2. Okay. And so if you want to give this a go, you could go ahead and try it out. And I'll go ahead and you could pause it and go ahead and give it a go. And then I'll put solutions here for you to watch. Okay, so there's our first step. And again, the claim is the alternative. And then here we have our second step, so getting our stats and data. And again, we kind of already did those calculations. That was the key thing I wanted to point out here. And so there is our graph here with the values, again, using the calculator. And notice I didn't get the chi-square critical value in case I don't have the 200B program, but we technically don't need that. There we go. And so this would be our fourth step there. Okay, p-value less than alpha, so reject and all. So we could say something along the line that there's sufficient evidence to show the number of pet distribution is different in this case. Okay, so I'll leave this up here for you to kind of go through. The key thing I wanted to illustrate here was how to get the expected and observed when they were not given to you directly.